My name is Jesús Barrasa, and I work for Neo Technology, which is the company behind Neo4j, the graph database. So I'll be giving you a gentle introduction to graphs and graph databases, and how they can bring value in your data initiatives, and specifically in the space of metadata management and data governance, right? So let me start with a very quick show of hands. How many of you have heard about graph databases? Neo4j, maybe? Oh, that's good. Right, so my plan was to do a brief introduction for those of you who are less familiar with graphs and graph databases, which are the key use cases that we find in our customer base, and then focus on metadata management and data governance, and talk about a couple of companies that are using Neo4j for that purpose, specifically in the context of the GDPR. So, first of all, what is a graph? So, a graph is a way of representing data, a way of describing data. Sometimes we find ourselves explaining how graphs are not necessarily charts, so it's not about representing data in a pie chart, in a bar chart. Is a way of describing data, and in the form of connected entities, connected data points. But why do we represent data as a graph? Well, for quite a long time, data has been, in a way, pretty boring, right? It was predictable, it was well-defined, and graph databases were great for that, because data was collected through forms, it was used to produce reports, and the table-based approach of relational databases is perfect for that. Now, the problem is, these days, data is a lot less predictable, is a lot more variable. It comes through us through many different channels, it's much more heterogeneous, and requirements change a lot more frequently than they used to. So we need a more flexible approach to representing data, and that's where graph databases come into play. So the graph databases, if you want, fall under the NoSQL category. So it's this set of stores that are an alternative to traditional relational storage that have a number of characteristics that fit very well in this dynamic scenario. And one thing that we find is that there's a category of problems where the connections between data points is equally, if not more important than the data points themselves. And at analyzing these connections, these dependencies, these relationships, is where graph databases excel. So what does it look like? How do I model data as a graph? How do I represent and describe data as a graph? We're going to use the property graph model, which is the one that Neo4j implements. There's a number of ways of representing graphs, formally and querying them, but this is the one we use. And in its basic form, a graph is, as I was saying before, connected entities, connected data points. So it has a strong foundation in mathematics, so there's the whole graph theory around it. But a graph is a set of data points that are connected to each other, data points connected to other data points. So the building blocks of a graph will be nodes, called data points, and relationships that connect them, or vertices and edges, if we use the formal mathematical terminology. So, but these graphs can represent anything virtually. So the graph model is very simple, because it's just based on these two very intuitive concepts, but it's very flexible and very powerful, because it can model anything. And we can think of a graph representing roads with traffic information, with traffic lights. We can think of a graph representing a hotel room offering with information about availability. It can be a graph representing individuals connecting together, and that's probably one of the most popular use cases if you think of social networks or professional networks. So this way of looking at data, where we have people knowing people, people following people, well, there we have the main elements. We have the nodes, we have the relationships between each other, and we have the notion of property. A property, or a list of properties, is a set of attributes or characteristics that describe both nodes and relationships. And that's specific of the labeled property graph that I'm describing here. So what's interesting about graphs is that they don't have the rigidity of the relational model, so we don't have to define what data looks like up front. So we can keep bringing entities, we can keep connecting our data and making our graph grow. And in that way, individuals can be connected, but they can be also connected to institutions, they can be connected to other individuals. And it's when this structure grows, right, at scale, that it can become a super powerful platform from which you can derive real value. So let me give you an example of, because you may say, okay, I have my data, how do I put that into a graph? What does it look like? Let me give you a very simple example. I'm sure you all have worked with Excel. So this is probably a very simple data set that contains transactions, so money being transferred, for example, between individuals. So we have from, to, an amount, and a timestamp. So if we have this data set, we can do things like finding who are the biggest senders, the biggest receivers. We can do aggregates. We can do the usual charting that we've been doing for a long time. But let's take this same data set and let's represent it as a graph. So this is exactly the same data set, but now we have the individuals that are sending money to each other, and each of the arrows represent one transaction. So immediately you see that the data starts talking to us. So we see structural patterns emerging there. So we immediately see that there are two clusters, if we can call it like that, or at least two separate communities, which was not obvious from the previous analysis. We can see that there are nodes that are more central in the cluster. There are others that act as the bridge between two subclusters. So there's a lot of structural analysis to be done on data once it's been modeled as a graph, right? In this simple step. Right, and who has done that before? Well, this shifting from thinking in terms of sets to thinking in terms of connected entities. Well, a number of companies that have become leaders in their space. So if you think how web search was a few years ago before Google turned up, what happened was that all the search engines were crawling the web, finding keywords, and they were offering some kind of UI to the searchers and then return the results. And they were ranked based on whatever they thought was relevance. And relevance could be, well, the fact that the term that you were looking for appeared a number of times in that page, as opposed to others. But then the Google guys had this brilliant idea of thinking, well, pages on the web are connected. They're connected through hyperlinks, right? And these hyperlinks, in a way, can be a way of representing relevance. So if a page is pointing to another page, if many pages are pointing to one page, it means that this page is important and therefore should have a higher rank. Okay? And this is something that can be applied recursively, transitively. So if an important page points at another page, that makes this third page even more important. So this simple algorithm that they call PageRank is what made Google, right? So, and now, of course, they are the most successful advertising platform in the world, among other things. But what they did is, instead of looking at documents, instead of looking instead of analyzing the data discretely, they looked at connections between elements. And this information was there, because it's the hyperlinks, pages that were connected already. All they had to do is analyze and propagate this relevance, right? So that's what they did. Something similar happened in the job professional networks space. So if you think how job search was a few years ago before LinkedIn, it was all about describing positions and putting them in some kind of store and offering search on top of them. So you could search for keywords on a particular skill or a particular technology and find which were the matches. But LinkedIn realized that, well, that's not exactly the way you look for a job. What you do is you probably look at your network, you look at the people who you work with in the past, you look at the companies that you might be interested in, technologies that you're interested in. So it's more like a network of connected entities. And of course, they became the leaders in their space. Something similar happened with PayPal. So this is a number of examples of large organizations that have made this change, they did this change in the way of looking at the data and became successful by looking at it as graphs. So Neo4j, our company, actually, none of us are Google or LinkedIn, these large companies. What Neo4j brings is an out-of-the-box solution that you can use to look at your data as a graph and start building and deriving value from it immediately. So, and we're seeing graphs being used in virtually any industry, so finance, social networks, healthcare, telecommunications, retail, anyway. I'm going to actually describe 3 or 4 of the key use cases that we keep finding in our customer base. And the first one will be real-time recommendations. So if you think of the scenario where you're doing shopping online, and in the time between the moment you put something on your basket and the moment that you get a recommendation, this short space of time, what a recommender system will do, well, ideally, if it's based on a graph, is look at what all the similar customers have done in the past. based on, for example, what the products that you're interested in at the moment or you have in your basket. You might also look at the stock and see if the products are available. You don't want to recommend something that's not available. You might look at product catalogs, product categories, and recommend similar things, not necessarily the same thing that other people has purchased, right? So modeling this as a graph and exploring it in real time is a way of producing highly relevant recommendations. And that's what, for example, Walmart is doing. So if you go to the Walmart website, Neo4j is running behind the scenes the recommendations that the website is producing. Another interesting use case is master data management. So master data management is all about bringing data from many different sources and coming up with a unified view, a single view of the truth. And sometimes, it's a lot about this customer is J. Smith, this one's John Smith. The names are reasonably similar. You might want to merge them together. What we're doing with graphs is we're transforming this discrete analysis into a structural one. Now, John Smith works for this company, and this company is a parent company of the other one. So you can do a structural similarity that makes this whole data integration and master data management a lot more accurate. And that's what, for example, Cisco are doing in the hierarchy management platform. Another interesting use case is fraud detection. So again, fraud in its most basic form is about detecting outliers, detecting things that are unusual, detecting transactions that happen at the wrong geography. So you're using your credit card because you're traveling to the US and it gets blocked because it's not the area where you normally use it. Or you do a high payment and it requires an extra level of validation because it's outside the range that you normally do payments. So this is fine, and that's probably the simplest from a technical point of view, but it's also the less accurate and the one that produces more false positives. So, and also, fraud is becoming much more sophisticated, and sometimes fraud involves looking at a number of individuals working together and looking at structure things. For example, this example of first-party fraud, where we have this group of fraudsters collaborating together and sharing means of identification to get access to lines of credit and then disappearing. We can elaborate a little bit more on this case, but this requires more structural analysis of your data, and that's something you can do with graph databases. And don't have names because customers tend to be very secretive about what they're doing, but it's one of the key use cases. Network and IT operations. If you think of networks, it's connected entities, it's a graph. And modeling dependencies, what depends on what, what's running on what, is kind of a natural thing that you do with graphs. And answering questions like what's going to be affected by a change. I mean, I'm updating this hardware. Which are the systems that are going to be affected? Which are the customers ultimately that may be affected by this downtime? So that's something that you can analyze by purely exploring your graph. And that's what, for example, HP are doing with the root cause analysis platform that's embedding Neo4j. Finally, another interesting case, identity and access management. So being able to define in a flexible and dynamic way who has access to what when people and users are organizing complex hierarchies and assets are also organizing categories. Being able to keep that up to date is not an easy problem. And that's what, for example, UBS and Telenor and many other companies are doing using Neo4j. Right, so I hope that's giving you an idea of the kind of use cases that we find graph databases, and in particular Neo, being used. But I'd like to focus on the data governance and metadata management space. And we have identified 4 graphs, as you would expect, of course, being a graph database, in this space that I've named data modeling and definition, data transformation, application and infrastructure inventory, and entitlement. Let me show a little bit about them. So what do I mean by graph? The graph about data modeling and data definition. So you typically have your enterprise ontology, your glossaries, your vocabularies, and then you will have a whole bunch of systems, siloed systems, that will implement these high level of conceptual entities. So being able to model and keep up to date this connection between the physical databases that are implementing logical models that ultimately refer to your enterprise ontology is definitely a valuable thing that you can use graphs for. So be able, for example, to answer questions like, what are all the different incarnations of the customer address in all my systems, right? According to this particular ontology. That's the kind of question that you can answer with this sort of vertical lineage, as we call it sometimes. And we have the equivalent, which is the horizontal lineage, which is about data transformation. When you're moving data from one place to another, let's say from an operational system into a data warehouse through some kind of middleware, that can be some ETL, some data virtualization, whatever the process is, that can be, again, described as a graph. And we can do it at the business level view, where we can specify key entities or critical data entities and how they're sent between systems. Or we can store and represent the detail of how specific columns or specific fields are being used and transformed through these middleware processes into enterprise data warehouse. And the kind of questions that we want to answer in this scenario is, well, I have this report that's producing a particular value for a customer. Where does that come from? What kind of transformation? What's the ultimate source? And which were the transformation along the way? So that's what we call horizontal lineage. That's another interesting case. The third one is about infrastructure and inventory. It's similar to the IT that I mentioned before. So you want to know where your applications are running. So sometimes, and well, these days more than ever, you have all sorts of virtualized hardware that's running on physical systems that are running, well, your billing, your enterprise data warehouse, et cetera, et cetera. So you want to know what things depend on what, not only for IT and fault management use cases, but also, for example, to be able to answer quite simply, are we paying too much to this database vendor? Are we having too many instances, too many unused instances of this particular software? And finally, the entitlement that I mentioned before. So the complexity involved in organizing users and assets in groups, modeling exceptions, is again something that can be accommodated in an easy way in a graph. So be able to, again, in real time, as a user logs in, what kind of assets or the list of things that he or she has access to is something that's modeled naturally in a graph. Okay, so of course these four don't live in isolation. They will live together and typically be used to build a unified view of your data. So let me talk very briefly about 4 examples. Couple of them, one of them, not 2 of them, I was involved in personally. So this one is one of the big 4 banks here in London. And what they were using Neo4j for was to model metadata in order to be able to answer lineage questions for GDPR. So what's interesting about them, and so I've described what a graph, a dependency graph may look like in the metadata management space, but one of the typical difficulties that you'll find is where do you source your data from and how do you keep it up to date? And what's interesting about them is that they had this application performance management deployed in their organization. It was not intended to be used for that, but as this application was monitoring the performance of the different systems, the different APIs, the different data stores, and the different elements interacting in the network, it also built sort of a topology of the elements involved in the data architecture. So they were able to detect that this API is getting data from this database, and this API is being queried by this front-end system. And we use that as the source of data to bring into the graph this sort of topology view. We enrich that with data classification information. For example, what's highly confidential, what's customer data. And also enrich with database schema information. And that produced this unified view of the metadata, and that was used to answer questions around data lineage. For example, where is this piece of customer information being used? Which are all the front ends? Is that used in the mobile channels? Is that used on the web channels? And things like tracking changes. When a new data set was added, a new data source was added to their architecture, what was the impact to all the system? Or when it was decommissioned, when it was removed, which are all the reports, which are all the applications that are affected by this change? Questions around impact analysis. That's one of the examples. The other one was not on the metadata side of things, was more on the pure data, and it was about for a large global information service group. And they were trying to answer complex questions around identity and consent management. So the kind of questions that they wanted to answer is the ones that you see on the screen. So when they want to contact someone for a particular campaign, can we access this person for this particular purpose? Or when the question came from the other side, from the clients, sometimes asking on behalf of the customers, tell me all the information that you have about this particular individual. Can they be removed from that particular list? And more from a product management point of view, from a data set point of view, they wanted to know what was the impact, for example, of removing a whole data provider. So these sort of questions are, again, the ones that we're working on. Finally, I just mentioned a name that came up in the last minute, but it's this company Trust Hub that are embedding Neo4j in their Business Lens platform, which is a platform that monitors how your customer data is used and identifies potential risks in compliance. So another interesting example. Good. Well, so if you have to, I mean, probably if you have to leave this room with 2 or 3 ideas about why graphs are relevant, I think I'm probably just giving you a brief overview of it. But the 3 key things I would say are their intuitiveness, the speed, and the agility. So the intuitiveness, I mean, I've shown some of the models, but and that's feedback that we get quite regularly from our users and from our customers. Modeling data as a graph is kind of a natural thing. I mean, if you query a graph with a query language, you will see that it's very close to the way you logically model a domain, the way you would whiteboard it. So this kind of whiteboard friendliness, as we call it, is one interesting feature that simplifies communications. That's one thing. The second one is the speed. And if you're modeling data in a scenario where connections between data points is relevant, where the kind of things that I've been talking about are relevant, graphs are your approach. And you will get speeds and performance that you won't get from any other non-graph approaches. And well, we have a quote here from one of our customers that reduced dramatically the query performance for a real-time scenario, like in the orders of thousands of times. So finally, the agility. I was mentioning before that a graph will grow organically. You don't need to define upfront what your data looks like. So a graph structure, NoSQL stores, will accommodate change, will accommodate new data sources, and that will bring lots of benefits, and especially from the point of view of reduction in the time to solution and time to market for your solutions. Neo4j comes with a query language that's specific for graphs, that's ASCII art based. I think we have a very quick example here, but we like to use this, especially when we're modeling dependencies. We find ourselves in a situation where we have to navigate multiple layers, multiple levels of dependency, transitive dependencies, and that involves in SQL doing a lot of self-joins, which is not particularly nice. I mean, it's probably a particularly pathologic example, but code tends to be complicated and performance gets degraded. So the same sort of thing will be expressed in Cypher in a much more graph-oriented way, in a much more structure and pattern-based way. And that, of course, less code to maintain, less code to debug, less code to onboard new members in your team, and a much more intuitive approach to data modeling. So I think I'm going to end up here. I don't know how I'm doing for time. Probably good. OK. So just to conclude, I mean, the analysts are on our side. Of course, they do their forecast. And one of the things they say is that graphs are a key differentiator in a number of data management spaces, but also that by the end of next year, 70% kind of is aligned with what the number of hands that were raised at the beginning of the talk. So we talk about 4 graphs in the metadata management and data governance space, but of course, this is an open platform. Your graph might be the next one. And, well, I hope that was useful. And thank you. If you have any questions, I'm happy to answer them now or at the booth. Yep.
If we go back to the slide that had your first use case that you examined.
Was that the one about recommendations? Or the one on
the one that had, no, this is not that far back.
Metadata management? Oh, the use case, you mean the...
Yeah, the use case. Yeah, this one.
Yeah.
I'm just, I want to understand the maintainability of this proposed architecture.
Sure.
At first glance, might be completely wrong there. There is still an element of technical, large technical input going forward, as well as a certain level of manual intervention with the Excel sheets as well.
Well, the reason why this data in the first place comes from a spreadsheet is because that's the way in the bank they were storing this kind of information. But probably you mean from this the technical effort, you mean more from the point of view of integrating this application performance management solution and the graph and this data? Are you talking about data ingestion? Is that Yep.
Keeping that model updated.
Sure.
Yeah.
Well, that's.
If there aren't any changes in any of these
Yep.
line systems.
And that's precisely, I mean, this is a dynamic connection. This is not, that's one of the problems, one of the main problems in metadata management. If you connect to any kind of tool that could be a bridge between, that could unify schema information metadata from your systems, keeping that up to date or doing this ingestion up to date can be, oops, that might be a fire alarm, so just on time. But what's interesting about this approach is that this is a totally dynamic and precisely takes that into account. So this is monitoring the network and it's constantly picking up new elements in the graph architecture, in the data architecture, right? So this is its purpose, is, as I was saying, is identifying bottlenecks, identifying problems in performance, but it also, and as a byproduct of that, it builds a topology, and that's kept up to date. So this is a totally automated, I mean, it requires, of course, some IT work in order to communicate that, but it was a pretty simple REST interface request to this is App Dynamics, actually. I don't know if you're familiar with it. But, and it's updated on a regular basis, and that way you kind of have the guarantee that you will have a real-time picture of what's in your data architecture, as opposed to, for example, what's documented, which is another of the problems when you try to model that out of static data. So answering your question, there's some degree of effort implementing this connection, but it's a one-off. I mean, it's API-based, and that will bring changes into your graph. And, of course, you will have to model into your graph things like change, things like tracking, and things evolving. But I see this particular approach and this particular architecture one of the most solid from the point of view of absorbing new changes. It builds a dependency, and if I have to be honest, that builds a dependency on this other product, but that's the one that will take in charge the responsibility of gathering all this information, which is basically what it does with a number of sensors across the different layers of their architecture. And so
I guess follows on that question regarding the proposed graph database there.
Yep.
Is that a persistent physical duplicate view in a graph format of the underlying database or databases?
Yep.
Or is it only a semantic metadata layer?
Well, Neo4j is a data store, and it persists in disk, and it's ACID compliant, and so it's a data store, and it will persist, keep whatever you store in it. In this particular case, we're modeling metadata, so we're not modeling all the data that transits across the network, but we're modeling there is a dependency, there is a connection between this API and this underlying backend, and there's JDBC traffic between the two of them, or there's HTTP traffic between the two of them. So you're not modeling, you're not storing and replicating into the graph every single bit of information that goes across that connection, but it's more like a dependency model that then will make it possible for you to answer this front end is presenting customer confidential information that's coming from this end store, and that goes through all this channel, through all this path, all this set of, so that's, but answering your question, yes, this is a store. It's not a virtualized view of data coming from different systems. It persists it, and that's.
But it persists only the semantics. So if I'm running a query against it, I'm presuming we can run a query against it.
Uh-huh.
It will hit the underlying online operating system.
No. It's a data store. You can run a query on it. Cypher is a query language, and it queries the data store. Now, if you want to add an extra, let's think, for example, I think where you're going is we want to keep the metadata at this level, but still combine the results of this metadata with querying the underlying system. And you might find an architecture where you have, on top of Neo, for example, a data virtualization layer that queries both the metadata and eventually the data from the underlying systems. But Neo4j as such is just a graph database, and it queries and the data that stores in the graph database. Does that answer the? Okay, thank you.
So I think graph presents a really powerful opportunity. I think when you go through a project, you probably build up quite a vast graph. How do you go about engaging your end user
Well,
get them to find use cases for it?
sure. Well, the thing is the graph is very different from the relational in the sense that you don't have to define what data is going to be like and then have to go through costly migrations whenever there is a change. So a graph is a model that accommodates change in a very natural way, and refactoring, evolving your graph is something that you can do in a very natural way. Then the other part of that is that probably the view that your end users have that's not necessarily to be the whole graph. I mean, there will be some kind of layer, some application level UI that you will build that will expose the portion of the graph. It's not always necessarily the case that you will expose graph to your end users. I mean, you might not show the graph at all. I mean, in this particular case, you might want to say there is a risk associated with the fact that this data is being used in your mobile front end coming from this source, but you don't necessarily need to present that as a graph. There is, of course, this possibility, but it's not always the case. So to answer your question, I mean, the graph can accommodate a number of models that coexist and that can be queries according to many different dimensions, and it can also evolve over time as the requirements evolve.
So if you take a fraud analyst who's looking for, you gave an example earlier, what guidance do you kind of give to them about where to start?
Sorry, what was the question?
So you mentioned, use cases,
Yeah.
fraud detection.
Yeah.
So you've got a fraud analyst.
Yeah.
You've got access to this. What recommendations do you give?
To fraud analysts, well, that's a completely different. Well, in the fraud scenario, there's two typical use cases. There's the automated one where you want a fast database that can answer in a probably in a sub-second space of time, like can I approve this transaction? Can I approve this application for a line of credit for this user? And all you want to do is a structural query that returns a yes or a no, saying this individual is involved in a dodgy ring, so please put that on hold, or maybe not, and then it can go ahead. But then the other case is the purely fraud analyst case where they're probably exploring, looking at, visualize the graph and looking for cluster, looking for visual representations of unusual elements. So the two typically coexist. I'm not sure I'm answering totally your question, but okay.
Okay. I think we've run out of time now.
Sorry, yeah.
Thank you very
Thanks.
much for that. I think that was super. Thank you.